Okay, thank you very much, Professor Grimm, for this excellent overview about the history of photogrammetry here in Germany. So you see we have about 150 years of history in photogrammetry, and we saw that it would be worthwhile also to give the audience of the CyArk Summit 2015 this presentation. So I want to continue with modern photogrammetry, and therefore I entitled my speech as Modern Photogrammetry and Cultural Heritage. So last 10 years we have seen a renaissance in photogrammetry. So you have heard yesterday this very good paper given by Matthew. He was talking about crowdsourced 3D reconstruction. So that means we can use images which are stored on the internet. We can download it via Flickr, Picasa, whatsoever, an image database, and we can use it. We can do some processing, calibration of the camera system, and then we use the images for Brandenburg adjustment, just to get the orientation and the location of the photos, and from this Brandenburg adjustment we get a sparse point cloud. And with the orientation of the photo, or with the pose estimation, as we call it in computer vision, we can feed dense image matching algorithms, and we get a very dense point cloud. So that means this combination of, let's say, using photos from everywhere, crowdsourced photos, calibrated and orientated, and then use dense image matching for point cloud generation is really a renaissance which has happened in the last 10 years. So you see here an overview where we can use photogrammetry. So Meidenbauer, for example, used it in architectural photogrammetry, object size of 10 meters up to 150 meters, but we can also do it in industry, so you can go down to 500ths of a millimeter if you like by photogrammetry, and you see here it is embedded in many methods of metrology. So what is the real advantage of photogrammetry? It's a non-contact measurement, so we can expose the object as a whole at any given point in time. So the photo can store all information about the object with high density. We can track moving objects. We can do everything automatic, as you will see later on. We have less efforts in our in situ fieldwork, and we have flexible data collection systems and processing, and we can do it online and maybe in real time. So the basics you see here, for those who are not that familiar, so we can just take one photo which is not usable for 3D reconstruction. For 3D we have to take the stereo photogrammetry, and you see here we need two photos, that means two stations, and if we know the rotation and the position of the stations, then we can easily intersect using the image points to the object space, and we get the known point in X, Y, Z coordinates. All is embedded in a global coordinate system X, Y, and Z. That means in a 3D coordinate system. Which systems, which cameras we use today? So we use today digital single lens camera systems. So you see here an early Nikon. So we can calibrate all those camera systems very precisely, but we can also use industrial cameras which are directly linked to a computer. There is normally no viewfinder, and this is a very robust system. Also, this needs calibration. We can also use smart cameras where there is software on the camera itself embedded in the camera, and we can also pre-calibrate the camera system, and we can do a lot of image processing on this camera system, and this camera allows also for real-time solutions. But we can also use off-the-shelf systems. Well, the Nikon was already one off-the-shelf, but we can also use the amateur systems like a Canon Ixus, a Ricoh, or whatsoever. You see here the Ixus, this was 280 euros, and the Ricoh is 1,950 euros. What makes the difference? So the difference I would like to give you shortly in one sentence. The difference makes the pixel pitch. That means is the size of every pixel. If you would like to have a good image quality, you should look for a pixel pitch of at least 4 micrometers. All those small camera systems which you see here, they have a pixel pitch of around 1.5, 1.8 micrometers, and also the smartphone cameras, they are around around 1.2, 1.5 micrometers. That means you have a lot of pixels, but if the image conditions, the illumination conditions are worse, then you have a very bad quality. So that means the pixel pitch is the driving force for a good image quality. Okay, but we can also use our mobile devices, iOS devices, a smartphone, iPhone, or an iPad mini or whatsoever, and we can also use Android devices to take photos, but we have to have in mind that those have to be calibrated. And most recently we can also use game consoles. You see here the Microsoft Kinect, which has also embedded a stereo system, which is consisting of an infrared projector, and next to it 50 millimeters is an infrared camera, that means which collects all the pattern of the infrared projector, and we have also an RGB camera just to texture afterwards the point cloud. So that means also here we made very good experiences using this low-cost device for 3D imaging. So but what is the main point? If you are using images from the wild whatsoever, the images have to be calibrated, and this is a crucial point. That means if you are really would like to have a precise 3D reconstruction, you have to have in mind photogrammetry. That means the collinearity equations, the equations between image space and object space with additional parameters, and we have developed all mass models just to calibrate all photographs which camera was taken ever. So no problem. So you see here we can model, physically model the radial distortion, tangential distortion, can also model non-orthogonality of axis, but there are many, many more effects, and though more effects can be modeled by additional parameters which we have developed in Fourier, by Fourier parameters and also Legendre parameters. So if we have the calibration and we have, for example, the pose estimation, then we can go into the multi-view stereo matching. We can do it hierarchically by semi-global matching, but in Stuttgart we use the multi-view stereo matching, and finally we get a very dense point cloud which can be used for true orthophoto generation and 3D CAD. And you see here an example how it works. So we make first of all the photos, so everybody can do it using his smartphone camera. Then you use the photogrammetric software like Visual SFM whatsoever. You get already a coarse point cloud, and then if we feed all the orientation and the locations of the photos into a dense image matcher, we get a very dense point cloud. You see it now. Then you can make a watertight model. You can triangulate all those points, and then finally you can put the real texture on it, and in this way every one of us can contribute to make a 3D reconstruction just using your smartphone, which you have always in your pocket if you use the right software. Okay, so you see the structure for motion is one, let's say, buzzword I want to explain. So for example, if we have many photos from different positions, that means we move around the object. So therefore, if we orientate all those photos and we make finally the intersection into object space, we get structure from our movement. Therefore, it is called in computer vision structure from motion, and there are open source algorithms available like Visual SFM, Bundler, whatsoever, which can be used by everybody just to compute this orientation. But not only we have to have in mind the, let's say, the movement around the object. The other important issue is that we have to use some feature detection in the images to find homologous points in the images, image 1, image 2, image n, and this is done by features. And here you see what we do with the features. So we have to find robust features in all the images which relate to each other, and also here we have very nice algorithms available from computer vision which find SIFT features, ASIFT features, but many more. And well, there is software available which matches the feature, and the final structure for motion is an approach which we call in photogrammetry bundle block adjustment, and computer vision is called, let's say, structure for motion, where we do first, we take all the images, we find the features which are homologous, which correspond to each other, and then finally we can compute all the pose, that means the orientation and location of the imagery. So you see here, recover the N camera projection matrices, P, which are the orientation matrices, with observed 3D points in object space and finally mapped in the image. So we have developed an own structure from motion, let's say, workflow in Stuttgart. So we do a lot of graph theory, but here is just an overview. There is a lot of math behind to solve everything automatically. But finally, you see here, we start first with all the analyzing the connection of images. Then we divide the image data set. We make a patch-wise reconstruction. And finally, we come out with a final bundle adjustment just to get all the information we need. And if we have the final bundle adjustment, that means the orientation, then we go into dense image matching. First of all, we create epipolar images. That means all those images which are lying in the epipolar plane. That means if we set up a basis between, let's say, the photo 1 and the photo 2 and the object space, that means we can use this epipolar imagery, which makes it easier to find the homologous points. So you see, if you have a stereo pair on the upper left and right, and then the lower image is the disparity image or the parallax image, which is found by a dense image matching algorithm. And this finally delivers a very dense point cloud. That means for every pixel in the image which is overlapping, that means which is available in the other image, delivers an XY set point, when we call point cloud. So the dense image matching, just to explain it to you, it's a very sophisticated approach where we have to minimize an energy function, and this energy function is just the difference in gray values between the left and the right images, and there are some penalty functions integrated over here. And so finally we find, let's say, the right image matching, the right image match for every pixel. That means pixel by pixel is matched, as you see here, and finally we can use all those matched images just to come out with, let's say, a very robust solution in object space. So we did a lot of projects in Stuttgart. So the first one was in 2011. We did together with Erwin Christofori, who is also here in the audience. So here we had to map this tympanum here on the west and on the east facade of the Royal Castle in Amsterdam. This is about 30 meters, and the height of the tympanum is 6 meters. And here we have taken for every tympanum 10,000 images, and we processed everything. So we used calibrated camera system, the GSD. That means the object resolution was less than 0.3 of a millimeters. So you see here 10,000 images have been processed, and I just would like to show you here the results. So that means here this point cloud is a point cloud of about 1.2 billion of points, and you see the quality of photogrammetry. There was no other technology available which could deliver this superb quality of the point cloud for the 3D reconstruction of the tympanum. The restorators were very, very enthusiastic about our approach. So 3 years ago, we went to Egypt. There is a new temple. There was a new temple found, a Akhenaten temple in Heliopolis in Cairo. And here we also used laser scanning and photogrammetry. We compared both technologies. And you see here a stone with hieroglyphs. And for this stone, we took in total 34 images, and with the Nikon DX2 40 megapixel camera. And we used our dense image matching software, Sure, which has been developed in my institute, and we created finally the 3D reconstruction, and you see here the comparison. This is a laser scan, the upper part, 1.4 million points. The GSD on the object is around 1.1 to 2 millimeters, and you see it here. So, but if I go to the image reconstruction, which is over here, so you see here, this is much more, but the resolution is much better, and you find all the details in this reconstruction using photogrammetry. I know it's a bit unfair because the resolution in of the images was around, let's say, 0.2 millimeters, and the other was 1 to 2 millimeters. But you see that in some cases, photogrammetry is really much better to be used than laser scanning. And here we did smartphone photogrammetry. A small sculpture was in a museum in Stuttgart. Here, one of my staff members took 195 images, and we reconstructed this structure. And you see, let me see where it is. So also here you can see, so you see Samsung Galaxy Ace delivering finally 23 million points. And you see here there are some gaps between not all, let's say, parts have been taken, and now we have developed a new app for a smartphone that you can directly control this point cloud on your smartphone. Then you can take more photos from those regions where we have some gaps, and so therefore we can also provide the complete coverage of all this sculpture. So when I was in February in Oakland in CyArk, and I met Ben and also Liz and Scott, and we were discussing about the CyArk 500. And the idea was born that we should start with a pilot project here in Berlin just to make a feasibility study to compare laser scanning and photogrammetry. And this was the idea that we could do the work. And we did it in end of August this year, and a couple of weeks ago. So my staff members, Chance Kuffenauer and Jose Balzar, met Scott Lee here in Berlin. Scott, they did first the scanning with our P20 from Stuttgart, and then we did a lot of photos. So you see here, we completed everything in 3 days. So you see here the reconstruction, first reconstructions using photogrammetry. So 2 software packages have been utilized, Agisoft Photoscan and also our Shure software from the Institute. So in total, we processed 1,270 images. We used dense image matching, and you see here already the result of the reconstruction, which looks quite nicely, and those blue markers just indicate all the photos which have been taken. And what might be interesting for you is this relief was reconstructed using a zoom lens, this object was in a distance of 10 meters, and you see all the details of this sculpture on the Brandenburg Gate in an excellent quality. So in my opinion, you see what meantime we registered all the 85 laser scans, and now we are processing it, the point cloud, just to come out with a CAD model you see over here, but this will take a while. But finally, we'll come out with this feasibility study. Here we are looking for the time for the in situ data collection, the time for the data processing, comparing accuracies, the object completeness, and also what about the necessary expert knowledge. And finally, what I have in mind is to deliver CyArk, the CyArk 500 photogrammetry kit. That means this must be or should be a DSLR camera, a Nikon, Canon, which is pre-calibrated, a computer, maybe Microsoft Surface Pro X3 or 4, or an Apple computer, software on the computer, and also the Android SFM running on the computer, and also the Android 3D app, just to check if everything is complete. And this kit can be used by everybody. That means this would be a great contribution to crowdsource data collection, so there is no need anymore to send the scanner to Syria, to Iran, to Iraq, whatsoever. Here we can send this small kit, and all people who are interested can use it and can try to document as much cultural heritage as they could do. Okay, conclusions. Photogrammetry has become easily applicable. The photo shooting with, I say always, calibrated smartphones and off-the-shelf camera is easy to do. The pose estimation, that means orientation and precision, can be done by structure from motion. The output is a sparse point cloud. With the oriented photos, we go into the dense image matching software, and we get a colored dense point cloud. The accuracies, so we have in X and Y, is around 0.2 GSD ground sampling distance, and in the depths we have around 0.5 ground sampling distance. Mobile apps will grow. We have already on the internet some Autodesk 1-3D catch about our Android SFM, and the trend will be to have standalone processing, maybe on mobiles only. The results, fully textured point cloud, superb quality for cultural heritage objects, and I guess with photogrammetry, so the next challenge of the CyArk 500 will be overcome very, very soon. Thank you very much for your attention.